The Earth's self-rotation period is 24 hours. What are the angular velocity, velocity of an object on equator, and the centripetal acceleration of such an object? The Earth's radius at its equator is 6.38 times 10 to the 6 meters. This should not say meters per second, that's a little typo, so ignore the second. So, to find out the angular velocity, we can use this equation right here. This states that the angular velocity is equal to 2 pi over the period. This is derived from angular velocity being equal to 2 pi times the frequency of the spinning object, which is basically 2 pi is the length of one rotation times however many times per rotation. And the period is just the reciprocal of the frequency. It's how much time to complete one rotation. So this is simply the equation that we will use to solve for the angular velocity. So the angular velocity is equal to 2 pi over the period in seconds. So the period is 24 hours. Now we can quickly convert that to seconds. 24 hours. And if you convert this by multiplying by 3,600, you should get that it's equal to 86,400 seconds. And that's how many seconds are in a single day. And so we can just plug that into the period. That's the amount of time it takes for the Earth to rotate one time. So 86,400 seconds. Now if you compute this, then the angular velocity should be about 7.27 times 10 to the minus 5 radians per second. And that answers the first part of the question. And now, let's move on to the velocity of an object on the equator. So we solved for angular velocity first because it allows us to plug the angular velocity back into this equation, which says that the velocity is equal to the radius times the angular velocity. So it's the distance of the object to the center of the circle. So you can just simply plug that in. The velocity equals the radius, which is 6.38 times 10 to the 6 meters per meters. 6.38 times 10 to the 6th meters. And then multiply it by the angular velocity, which is 7.27 times 10 to the minus 5 radians per second. Now, again, if you plug this into a calculator and compute this, you should get that the velocity is about 464 meters per second. And that is probably over 900 miles per hour if you convert it. And that is the second part of this problem. Now the final part, we need to find out the centripetal acceleration. Now, the centripetal acceleration can also be represented by setting it to equal to the radius times the angular velocity squared. But if we convert it, we can also switch it to this form, where the centripetal acceleration is equal to the square of the velocity over the radius. And this is done by simply showing that solving this equation for the angular velocity, so that the angular velocity is equal to the velocity divided by the radius. And if you plug that back into here, that should give you this equation. Now you can use either one, but I'm just gonna plug this in since I don't have to write as much. So the centripetal acceleration is equal to the velocity squared, and this is not angular velocity, this is regular velocity, so 464 meters per second squared over the radius of 6.38 times 10 to the 6 meters. Now if you solve this, you should get that the centripetal acceleration is equal to 3.37 times 10 to the minus 2. meters per second square. And that is your third answer. You can also write this as about 0.0337 meters per second squared. This is before you turn it into scientific notation. And that is a really, really small acceleration, so it's really just not noticeable at all. And that is the answer for the third part of the question.